Hi everyone. So in the last video we learned about the different strategy of creating the structural properties of a convolutional encoder, right? Encoder. That is, we know that using convolutional encoder we can represent convolutional encoder using a state table. Then you can represent convolutional encoder using a state diagram. You can represent convolutional encoder using the tree diagram and also using the trellis diagram, right? So now in this video we are going to learn about a very simple topic, and here what we are going to do is we are going to learn about the decoding of the convolutional codes. The decoding. So decoding of convolutional codes means, see, in this case they will give you the received sequence, or the receiver will receive the sequence, and then from the received sequence you need to find if the sequence is correct, and if the sequence is wrong, then you need to find the right sequence from the received sequence, and that process is what you call as the decoding of convolutional codes. Okay, and the type of decoding of convolutional codes that we use here is called as the maximum likelihood decoding of convolutional codes. Okay, so that is the maximum likelihood decoding. So what is maximum likelihood decoding of convolutional codes means? Here you apply the log likelihood function. You find the value of the log likelihood function, and then you apply the log likelihood function to every stage, at every stage. And which stage are we talking about this? I'm talking about the trellis diagram. Okay, that is the best, because the trellis diagram, one of the advantage of trellis diagram is that we can apply the log likelihood function at every stage, and then you need to compare every value of log likelihood function at each stage, and then you find the maximum possible value of the log likelihood function. By comparing the values of the log likelihood function, we can find out the correct sequence from the received sequence. That entire process is what you call as the maximum likelihood decoding of convolutional codes. And the algorithm used for applying this maximum likelihood decoding is what you call as the Viterbi algorithm. That is, the spelling is Viterbi algorithm. This is the algorithm that is used for applying this maximum likelihood decoding. Okay, so that's the general aspect. Let's look into detail how we look at this. All right, so first what we do is, suppose that an information sequence U, okay, has length of KL, right? KL. The reason why we are applying KL is because it may not be, sometimes the value of K may not be 1. It can be more than 1. So in that case, the information sequence is U1, U2, U3 up to UL for length KL, right? So in other words, the information sequence will be from U is equal to U1, U2, U3 up to UKL. Okay, if the value of K is greater than 1, so this will be the length, your total length of your information sequence. Okay, and likewise, and if this information sequence is encoded into a code word V, where V is nothing but V1, V2, V3 up to VL plus M. And remember, and if the value of N is greater than 1, then the length of N is equal to N into L plus M. Right, this is the length of the output sequence, and we have seen that in the last video, right? The length N is N capital letter N, that's total length is equal to N into L plus M. Or in other words, I can represent the output sequence as V is equal to V1, V2, V3 up to Vn. Okay, and that is your output sequence. Now what I'm going to do is that I'm going to transmit this sequence, or this sequence. I'm going to transmit this sequence, and the receiver will receive this sequence. R is equal to R1, R2, R3 up to Rn. Okay, where the subscripts now simply represent the ordering of the symbols in each sequence. So just for our easiness, I represent U is equal to, in this form, that is my information sequence. And then the transmitted sequence, or my encoded sequence, I represent in this form. And then after transmitting this, I will receive this. Okay, so I will receive this sequence. Now what we are going to do, the main thing what we are going to do is that we need to make an estimate U dash of the, or U cap of the information sequence. That is your job. That is our job. Our main duty for decoding is to find the value of the estimate sequence. And to find the value of the estimate sequence, you need to find the value of the correct transmitted sequence, because for every input information sequence, we have a one-to-one correspondence with the transmitted sequence. Since there is a one-to-one correspondence between U and V, the decoding can be equivalently the one of making an estimate V cap of the code vector. So if you want to find the, in other words, if you want to find the correct information sequence, you need to find the correct transmitted sequence. And we already know that that we have only, the receiver has only received the received sequence. So if this sequence is correct, then from this sequence we can find the sequence, or in other words, we can find the sequence. And then we may put U cap is equal to U if and only if V cap is equal to V. That's the meaning of this. So that means we can only find the information sequence if the V cap, or if the estimate of the output sequence is correct, is the same as your transmitted sequence. And what happens if it is not correct? Or in other words, what happens if the received sequence is different from the transmitted sequence? Then there exists a decoding error. So therefore, what we do is, the decoding rule for choosing the estimate V cap given the received vector R is optimum when the probability of decoding error is made minimum. That is what you need to understand. For equiprobable messages means messages in which each the probability of transmitting of every message is equal. Okay, equal. So for those messages, it follows that the probability of decoding error is minimum if the estimate V cap is chosen to maximize what we call as the log likelihood function. So in order to make a least or the minimum probability decoding error, we need to we need to choose the maximum log likelihood function. Okay. So here, let P of R by V, right? P of R by V. We don't know what is the meaning of this, right? This is called as a conditional probability. So P of R by V means probability of the received sequence when we know what the transmitted sequence is. Okay. Let P of R by V represent the conditional probability of receiving R given that V was transmitted. The log likelihood function is represented by log of P of R by V. So what this means is that first we take, to understand this, first we take the value of probability of R by V, where probability of R by V is the probability that the received sequence is received. What is the probability that the received sequence is received when we know when we know V is transmitted? Okay, and to find, so what is log likelihood function? Log likelihood function is nothing but simply apply log to this value, that is natural logarithm of P of R by V. Okay, or you can simply write it as natural logarithm of P of R by V. This is what you call as the log likelihood function. So like I said, now you know what is log likelihood function, right? So what you are going to do is, we need to choose at every stage, we need to choose the branch, or we need to choose the node which has the maximum log likelihood function. Okay, we need to find out, or in other words, we need to find out the maximum value of the log likelihood function. If this value is maximum, then that value will be your estimate, and then that value is the value that you're going to choose as your correct transmitted sequence. Okay, so to find the correct transmitted sequence, you need to calculate the log likelihood, all the possible log likelihood functions, and choose the value which is maximum. Okay, so that's what we are going to do here. The log likelihood function is then log of P of R by V. The maximum likelihood decoder, or the decision rule, is to choose the estimate V when the log likelihood function as this value is maximum. That is how we are going to apply maximum likelihood decoding. Okay, this is generally nothing. So what you need to remember is this. All you need to remember is this. Maximum likelihood decoding means you need to find the value of this, that is a conditional probability of R by V, and then you need to apply log to it, which is called as the log likelihood function. And the decision rule is to find this value, all the possible values of this log likelihood function, and choose the value of which is maximum. So your output sequence corresponding to that maximum log likelihood function is your estimate or your correct information or your transmitted sequence. Okay, that's all. That's all. The only thing over here you need to remember is this particular value, and this value should be maximum. Okay, so that's what we are going to do over here. So for a discrete memoryless channel, okay, a discrete memoryless channel, we already know what a discrete memoryless channel is. That is you can consider it as a channel that transmits only discrete values, and also there is no memory involved. Okay, the two sequences V and R may differ in some locations because of the channel noise. Okay, with V and R as assumed, we then have the probability. So how do we calculate this conditional probability? P of R by V. How do you calculate this? This is calculated by P of R1 slash V1, that is the first bit. Okay, the first bit, we will calculate the probability of the first bit of the received sequence when we know what is the first bit of the transmitted sequence, then into the probability of the second bit of the received sequence, probability of the second bit of the received sequence when we know what is the second bit of the transmitted sequence, into probability of the third bit of the received sequence when we know what the third bit of the transmitted sequence is. Like that, we keep multiplying up to the value of n, right? Because the total number of values for both of them is n, right? N. So which means this, we multiply all this up to P of Rn slash Vn, the total multiplication of all this. Okay, or in other words, this can also be written as product of, use pi, product of from I is equal to 1 to n P of Ri slash Vi. This is how we calculate the log likelihood or the probability, conditional probability of R by V. That is the product of I is equal to pi of I is equal to 1 to n P of Ri by Vi. Okay, this is how we calculate it, right? That is what's written over here. Now what I'm going to do is then, accordingly, the log likelihood function becomes, that is, all you need to do is now you apply log likelihood function over here. So therefore, the log likelihood function of this is nothing but log of this value, which is nothing but the natural logarithm of pi from I is equal to 1 to n P of Ri by Vi. Okay, this is what we do. And then what we do is, we can apply this log inside this. So this will become pi of I is equal to 1 to n log of P of Ri by Vi. Okay, so which means, what this means is that the log likelihood function is nothing but the this is actually the summation of this is actually, when you say it, you see there's one mistake over here. You see, when you apply log over here, okay, when you apply, we already know what is log 6. Log 6 is nothing but log 3 plus log 2, right? Also we know that log 8 is equal to log 4 plus log 2. Also log 10, we take log 10. Log 10 is equal to log 5 plus log 2. In the same way, okay, if I'm going to apply the log to this function, if you're applying log to this function, then this product will become nothing but summation, right? This product becomes a summation. So which means this is not product, it's actually summation, okay? Or in other words, this is nothing but summation of I is equal to 1 to n log of P of Ri by Vi. Okay, it's not product, it's summation. Okay, because because every product, when you apply log to a product of numbers, it becomes an addition of numbers. addition of the log numbers. Okay, so that's what we see here. Now next what we are going to do is, let p, small letter p, okay, let small letter p be the number of places where the received sequences and the transmitted sequences are different from each other. Okay, suppose for example if the output sequence, okay, for example if the output sequence, for example, okay, if the received sequence is 1 1 0 1 1 1, okay, suppose if this is the received sequence and the if this is a received sequence and the transmitted sequence is 1 0 1 0 0 1, so in that case this is the transmitted sequence, this is the received sequence. So in that case, in how many positions are these two different? They are different over here in the second bit, they are different in the third bit, and they are different in the fourth bit and in the fifth bit, right? So which means then in that case the value of p is equal to 4. That is the meaning of this. That is the difference. P represents the how many positions are the received sequences and the transmitted sequences are bit positions. How many bit positions are these two sequences different from each other? That value is called as the small letter p. Okay, or in other words, we already know that there's another name for this. This is nothing but also called as the is it p or is it some other letter? No, it's not p actually, it's small letter d. Okay, small letter d. It's not p, we are using small letter d, and this d is what you call as the Hamming distance. Okay, this small letter d is what you call as the Hamming distance. This is called as the Hamming distance. So what we are going to do is that we are going to fix, okay, then that's one thing you need to understand. Another thing you need to understand, that is what's written over here, is we are going to need to understand is that we are going to say that we are going to state the value of the probability, the conditional probability of every bit. Okay, we are going to state the value of the conditional probability of every bit, and we are going to say that this value is equal to p, this value is equal to p when when the respective bit is not equal to the transmitted bit. For example, over here, and over here, you see they are different. So in that case, the probability of the values when they both are different is equal to p, and the probability of those values when both the received bit and the transmitted bit are the same is called as 1 minus p. Obviously, right? If this is p, then if this is the probability of the wrong bit of all the possible wrong bits, then this must be the possible of all the correct bits, 1 minus p, right? So so that's what it means. That is, if the bits are different, the probability of bits being different, the probability bit being different means that there is a mistake, right? Or there is a difference between the received sequence and transmitted sequence, and that probability is called as p. And if it is right, if both of them are same, then the probability is 1 minus p. Okay, 1 minus p. So in that case, then obviously we know that, see, if you look over here, obviously the total number of bits in both the sequences, we already know that the total number of bits is equal to capital letter N, right? The total number of bits is capital letter N, and we also know what is D. D is nothing but the Hamming distance, or the number of positions where they are both same, or sorry, but the number of positions where they are both different, right? That is the Hamming distance, or the on the positions where they are both different. And if you see here, the probability that when they are both different is actually p. So in that case, okay, in that case I can say that my total log likelihood, or my total probability p, right, the total probability p, or in other words the log likelihood function of this can be represented as, if you look over here, let the received vector r differ from the transmitted vector v in exactly d positions, then the number d is nothing but the Hamming distance between the vectors r and v. So therefore, like I said, the formula now becomes like this. Okay, that is, this is nothing but, that is log likelihood function p of r by v is now becomes, it used to be this value, right? So this value can now be written as sigma. Okay, there is this value right here. So now need to add sigmas. This time we're going to multiply this with this, right? So that means this becomes d into log p, d into log p, because that many probabilities position this difference, plus, and what about the remaining values? If this is the values where they are both different, the remaining values that they are not different is called as n minus d. Okay, and its probability is 1 minus p, so therefore it will become log of 1 minus p. This is how it looks like. Okay, this can also be written as d of log p plus this can be written as n into log of 1 minus p minus d into log of 1 minus p. Okay, I can compare the first term and the third term. So this will become d of, you can take d common, and this is nothing but, see, this is minus, right? So we can write this as log of, so they do becomes numerator and denominator. So this becomes log of p by 1 minus p, right? This can be written as d log of p by 1 minus p plus n into log of 1 minus p. That's it. Okay, if you see over here, there's a mistake. They haven't written the second term. Okay, the second term is n log 1 minus p. This is supposed to be plus n log of 1 minus p. Okay, this is how it should be. Okay, so this is what this is the value that you get. Log of p of r by v, that is your log likelihood function, can be represented in this way. Okay, and if you look over here, this term can be represented in terms of we call it as d a plus b, I think, right? This can be termed as minus a plus a d plus b, or you can write, okay, you know, write like that, minus d into a plus b. Okay, so, or this is how we can represent this. Or in other words, in this term, if you compare these two equations, when you compare these two equations, you can see for yourself that a is equal to, a is nothing but log of 1 minus p by p, and another, and b is nothing but log of 1 minus p, okay? So in both the case, a and b, both of them are nothing but constants. They both are nothing but constants, and if they are both constants, then the only thing that is variable is this particular value. This is the only value that is a variable value right here. That's the only thing that is variable. So in other words, okay, the only way to maximize, according to this equation, the only way to maximize this is to minimize this. In other words, in order to finding the maximum likelihood function, you just instead of finding the maximum likelihood function, what you need to do is you need to find the minimum Hamming distance. The minimum Hamming distance of the received sequence with compared to your transmitted sequence. You need to find which transmitted sequence has the minimum distance from the received sequence in order to find its correct sequence, in order to find the correct transmitted sequence. That's what it says here. So that's what's written over here. Here a is equal to, here they represent a is equal to minus log of, yes, supposed to be minus log p by 1 minus p, right? It should be minus log, yes, correct, right? Minus log of p of n minus p, or the same as this, and b is equal to n log 1 minus p. They both the value of a and b, both of them are constants. So therefore, since both of them are constants, The only thing that is different is the Hamming distance d, and that value should become minimum, right? So in general, the probability of error occurring is low without the loss of generality. We may assume that p is less than 1/2, and it follows that the constant a is positive. Hence, from the above equation, we can say that the log likelihood function becomes maximum when the Hamming distance d becomes minimum. Then we may state that the maximum likelihood decoding rule for a discrete memoryless channel or a binary symmetry, this is a BSC, right? This is a BSC channel, binary symmetric channel. So the decoding rule is this: choose the estimate v that minimizes the Hamming distance between the vectors r and v. So earlier what we said was choose the maximum likelihood function, right? But here now saying choose, we need to choose the estimate v cap that has the maximum likelihood function. But now we are saying, now our rule has been evolved, and now we are saying choose the estimate v cap that minimizes the Hamming distance. And this process is what you call as the maximum likelihood decoding. That is, maximum likelihood decoding is you don't need to apply the log likelihood function for everything. Okay, that's what we are saying here. You don't need to apply the log likelihood. Even if you don't know what the log likelihood function is, you still don't have to find. What you need to find is, you need to find the Hamming distance. And that is simple, very easy to find, right? Very easy to compare the Hamming distance. Just simply compare each output values, compare each output bits and see where they are different, and see which sequence has, which path has the least different bits. That's what you need to find here. Thus, for a binary symmetric channel of maximum likelihood decoder reduces to a minimum distance decoder. So you don't have to find the maximum likelihood decoder. You can apply the minimum distance decoder, in which you find the value of the transmitted sequence by finding out which sequence has the minimum distance from the received sequence. In such a decoder, the received R is compared with each possible code vector V, and the particular one closest to R is chosen as the correct transmitted sequence or the correct transmitted code vector. Okay. So here the log likelihood function P of R by V is called as the metric. The name would be called as the log likelihood function is also called as the metric, associated with the path V, and is denoted by M of R by V. The terms log of P R by V when I is equal to 1, 2, 3 up to L plus M. This term can be represented as M of R by V, and this is called as the branch matrix. And if this log of P R by V, in which I is equal to 1, 2, 3 up to N, then this function is also called as the bit metric. Right? So it can either be called as the branch metric or the bit metric, depending on what the value of I is. Okay. So this is how we represent the log likelihood function or the metric of the decoder. And a partial path metric of the first j branches of the path can be represented in this fashion. So that is, this is not complete, this is complete, but this is up to j. This is how we find this value. Okay. So but here the main point from your point of view, from the exam point of view, it will be less likely that they'll give you the log likelihood function, because then they have to give you all the respective log likelihood function of all the respective values, and that will be a little bit difficult to find. In that case, you'll be applying it, and then you need to calculate the log likelihood function for every value, and that process is tedious. What is more simple is by comparing it using the Hamming distance. That is actually much more easier. You don't have to sit and calculate this value for every stage. Instead of that, simply find the Hamming distance at every stage and then find its value. And that process was what you call as the Viterbi algorithm. That process is what you call as the Viterbi algorithm. So what is Viterbi algorithm is? Let me just tell you what that algorithm is. This algorithm is nothing but applying the function that you have studied before. That is, you are going to apply this method, or this method, whichever method chooses. Either you can apply the maxima, you can choose the Hamming distance method. That's you need to compare the Hamming distance and find the minimum value, or you can apply the log likelihood function and find its maximum value. Either way, but in both of the case, the algorithm that we are using here is to apply this is called as the Viterbi algorithm. And in this algorithm, the first step what we do is we apply the trellis diagram for this. We apply the trellis diagram, and what we do is I draw the trellis diagram up to M value, where M is the number of shift register stages. So I apply the algorithm up to M value, and then starting at level J is equal to M. Okay, J is equal to, where J is the time unit. Starting at level J is equal to M, I find the partial metric of the single path entering each state. And then I store the value. Okay, I store the path, and that path is considered as a survivor and its metric for each state. That's it. That's what I'm going to do. Then after this, I'm going to do this for the next state also. That is at the next time unit. Okay. At the next time unit, I will then compare. After the next time unit also, again, I will find its partial metric. I will find the partial metric, and then I'll increment the time again, and again I'll find its partial metric, which means I will find the partial metrics of every time unit. Okay. Compute the partial metric of all the path entering the state by adding the branch metric entering that state to the metric of the connecting survivor of the previous time unit, or the preceding time unit. Okay, so which means that you apply the partial metric of one state, then you apply the partial metric of the next time unit, and then you add it with your previous time unit. Okay, for each state, and then store the path with the largest, metric. You find the path which is having the largest metric, and that path is your corresponding information sequence, your correct transmitted sequence path, together with this metric, and eliminate all other matrix. Eliminating is done by putting a cross. Okay, whichever the path which has the lesser, we find what the value, we find the path which is having the maximum branch matrix. Okay, that is we find the branch matrix of every path of every time unit. We apply the branch matrix at every time unit, and then we add it with our previous time unit. So in that case, the value at every time unit, the value keeps increasing. Okay, at every time unit, the value keeps increasing, and then we find the path which is having the maximum metric. Now, if you are going to apply this on top of a Hamming distance, instead of here they are using branch metric. Okay, if it is a Hamming distance, then in that case you need to same story over here, but then instead of finding the partial metric, you find the Hamming distance of every single path. You find the Hamming distance, and then you store the Hamming distances of every path, and then you increment. When you are finding the distance of the next path, you find the Hamming distance, and you add it with the previous Hamming distance of the previous time unit, and then you add it together with your present Hamming distance. And when you add them together, what you do is you choose the path that has the least Hamming distance. You choose the path that has the least Hamming distance, and that path is the path of your correct transmitted sequence. If J is less than L plus M, repeat step 2, otherwise stop. So this is called as this is how we apply the Viterbi algorithm. Okay, so I know that by looking over here, I can show you one example of how they applied Viterbi algorithm in this textbook. Okay, here you can see as an illustration, this is what you can see for yourself. This is how you apply the branch. Here what we did is that we find this is called as the metric table, and these are the possible values of the branch matrix, and you can see the computations being done for every branch with respect to the trellis diagram. Okay, with respect to trellis diagram, this is our metric path that we used. This is nothing but what you call as the log of P of Ri by Vi. Okay, that is the values that you see over here. And then, but the thing is that by applying this way might be very difficult for us, because if you can see over here, all of them are all decimal numbers and negative numbers are also included. And once we know that these are all additive in nature, so what we do is, instead of applying this table, we modify this table, or we normalize this table into this table. Okay, so how we do is that so this is how we did. That is, you can see here there are 4 sets of values. That is minus 0.91, then we have minus 1.2, we have minus 2.3, and we have minus 1.61. So what we do is I replace these 4 values that you see in this table with these values. Instead of minus 2.3, that is the least value, so I represent it using the number 0. And then the next smallest number is this one, minus 1.61. So I replace that using another integer. You can choose your own integer. Here the textbook, they have chosen 5, and instead of minus 1.2, they have chosen the value 8, and instead of minus 0.91, which is the largest value over here, so here the largest value we will modify it as 10. The reason is because doing the calculation using this is much more easier than this. That is why we call this as an integer metric table. We're just going to represent this table using some symbol positive integers. And so what we do is we simply apply this computation for every, like I said, we apply the computation at every stage, and this is what happens when you are applying it in the trellis diagram. We compare these values at every stage, and you can see over here the path that has the least. Here in this case it's the log likelihood, so the path that has the small likelihood, only the one that has the largest log likelihood function, or the one that has the largest metric will survive, the rest of them will be discarded. So that's what I see here. You see here over here when you calculated the log likelihood function using the computation that you see over here, this is the computation, right? Using these two computations, you can see over here that the path over here is, the metric over here is 5, the metric over here is 18, and since this is smaller, we discard this because this is larger. And then what we do is we increment the time unit. Likewise, we increment the time unit, we compare all these values, okay? And some of the nodes has more than 2 metric. Some of them has more than 1 metric, 2 or more than 2 metric values. In that case also, we will just discard the one that has the smaller value. We only consider only the large value. Okay, that's what we do here. If you can see over here, every path over here is discarded except this value right here, because this has the why this is not discarded, because this has the largest metric value. If you compare of them, the rest of them are small. Here the metric value is 30. Here the metric value over here is 8. So you add this 8 with your previous metric value. So how much it is? 8 plus 5, which is 13. Here is 15. So 15 plus 5, which is 20. Here is 18. 18 plus 8 is 36. Here it is 5. And 5 plus 18 is 23. And if you compare over here, so the metric value over here is 20. Partial metric. The partial metric over here is 20, 13, 36, 23. Which is the largest value? This is the largest value. Therefore, you discard this, this, and this. This is how we do it, and you apply it at every stage. So that at applied at every stage, find the metric, discard, consider only the largest value and discard the remaining values, and like that we can find its metric. So at the end, you will get this kind of a diagram. Okay. This is the Viterbi algorithm. If you compare this, I want you all to just pause the video and see how this is being drawn. Okay, or instead, better yet, you know what, we will be doing a problem based on this. Okay, a Viterbi algorithm, just to familiarize with you. But this time, when I'm going to do the problem, I'm not going to apply this table, because applying this table is very tedious, right? And not only that, it is less probable for them to actually give you the table at the time of exam. What is much more easier is you apply the Hamming distance. Okay, instead of sitting and finding the value for all these metric values, you simply apply the Hamming distance. I will show you how it is being done. Okay, so this is what you see in this diagram over here. Okay.